Hello everyone, welcome to my channel. So today I'm going to start with a new series called Read With Me. So here I'm going to start with my first video, which is Physics Part 1 textbook for class 11. So if you are a student of 11th class, you can watch this video and get some help in your reading. So I'll be going to read out few topics from this textbook. Okay, so if we come here, we can see that what are the topics here. We have a number of topics. Today I am going to read this topic here, that is laws of motion. So in this chapter we have introduction, Aristotle's fallacy, the law of inertia, Newton's first law of motion, second law of motion and third law of motion, and then conservation of momentum, equilibrium of a particle, common forces in mechanics, circular motion, and solving problems in mechanics. So let's start with this. Okay, students, so let's start with the introduction. In the preceding chapter, our concern was to describe the motion of a particle in space quantitatively. We saw that uniform motion needs the concept of velocity alone, whereas non-uniform motion requires the concept of acceleration in addition. So far, we have not asked the question as to what governs the motion of bodies. So in this chapter, we turn to this basic question. Let us first guess the answer based on our common experience. To move a football at rest, someone must kick it. To throw a stone upwards, one has to give it an upward push. A breeze causes the branches of a tree to swing. A strong wind can even move heavy objects. A boat moves in a flowing river without anyone rowing it. Clearly, some external agency is needed to provide force to move a body from rest. Likewise, an external force is needed also to retard or stop motion. You can stop a ball rolling down an inclined plane by applying a force against the direction of its motion. In these examples, the external agency of force, that is hands, wind, stream, etc., is in contact with the object. This is not always necessary. A stone released from the top of a building accelerates downward due to the gravitational pull of the earth. A bar magnet can attract an iron nail from a distance. This shows that external agencies, example gravitational and magnetic forces, can exert force on a body even from a distance. In short, a force is required to put a stationary body in motion or stop a moving body, and some external agency is needed to provide this force. The external agency may or may not be in contact with the body. So far so good. But what if a body is moving uniformly? For example, a skater moving straight with constant speed on a horizontal ice slab. Is an external force required to keep a body in uniform motion? Aristotle's fallacy. The question posed above appears to be simple, However, it took ages to answer it. Indeed, the correct answer to this question given by Galileo in the 17th century was the foundation of Newtonian mechanics, which signaled the birth of modern science. The Greek thinker Aristotle, 384 BC to 322 BC, held the view that if a body is moving, something external is required to keep it moving. According to this view, for example, an arrow shot from a bow keeps flying since the air behind the arrow keeps pushing it. The view was part of an elaborate framework of ideas developed by Aristotle on the motion of bodies in the universe. Most of the Aristotelian ideas on motion are now known to be wrong and need not concern us. For our purpose here, the Aristotelian law of motion may be phrased thus: an external force is required to keep a body in motion. Aristotelian law of motion is flawed, as we shall see. However, it is a natural view that anyone would hold from common experience. Even a small child playing with a simple non-electric toy car on a floor knows intuitively that it needs to constantly drag the string attached to the toy car with some force to keep it going. If it releases the string, it comes to rest. This experience is common to most terrestrial motion. External forces seem to be needed to keep bodies in motion. Left to themselves, all bodies eventually come to rest. What is the flaw in Aristotle's argument? The answer is a moving toy car comes to rest because the external force of friction on the car by the floor opposes its motion. To counter this force, the child has to apply an external force on the car in the direction of motion. When the car is in uniform motion, there is no net external force acting on it. The force by the child cancels the force or friction by the floor. The corollary is, if there were no friction, the child would not be required to apply any force to keep the toy car in uniform motion. The opposing forces such as friction for solids and viscous forces for fluids are always present in the natural world. This explains why forces by external agencies are necessary to overcome the frictional forces to keep bodies in uniform motion. Now we understand where Aristotle went wrong. He coded this practical experience in the form of a basic argument. To get at the true law of nature for forces and motion, one has to imagine a world in which uniform motion is possible with no frictional forces opposing. This is what Galileo did. The law of inertia. Galileo studied motion of objects on an inclined plane. Objects moving down an inclined plane accelerate. You can see it in this picture here. While those moving up retard. You can see here in this picture. Motion on a horizontal plane is an intermediate situation. Galileo concluded that an object moving on a frictionless horizontal plane must neither have acceleration nor retardation. That is, it should move with constant velocity. Another experiment by Galileo leading to the same conclusion involves a double inclined plane. A ball released from rest on one of the planes rolls down and climbs up the other. If the planes are smooth, the final height of the ball is nearly the same as the initial height. A little less but never greater. In the ideal situation, when friction is absent, the final height of the ball is the same as its initial height. If the slope of the second plane is decreased and the experiment repeated, the ball will still reach the same height, but in doing so, it will travel a longer distance. In the limiting case, when the slope of the second plane is 0, that is, it's a horizontal, the ball travels an infinite distance. In other words, its motion never ceases. This is, of course, an idealized situation. So here you can, in this picture, they have illustrated this. The law of inertia was inferred. So the law of inertia was inferred by Galileo from observations of motion of a ball on a double inclined plane. In practice, the ball does come to a stop after moving a finite distance on the horizontal plane because of the opposing force of friction, which can never be totally eliminated. However, if there were no friction, the ball would continue to move with a constant velocity on the horizontal plane. Galileo thus arrived at a new insight on motion that had eluded Aristotle and those who followed him. The state of rest and the state of uniform linear motion, that is, motion with constant velocity, are equivalent. In both cases, there is no net force acting on the body. It is incorrect to assume that a net force is needed to keep a body in uniform motion. To maintain a body in uniform motion, we need to apply an external force to encounter the frictional force so that the two forces sum up to 0, net external force. To summarize, if the net external force is 0, a body at rest continues to remain at rest and a body in motion continues to move with a uniform velocity. This property of the body is called inertia. Inertia means resistance to change. Inertia means resistance to change. A body does not change its state of rest or uniform motion unless an external force compels it to change that state. Okay. Next we will see Newton's first law of motion. Galileo's simple but revolutionary ideas dethroned Aristotelian mechanics. A new mechanics had to be developed. This task was accomplished almost single-handedly by Isaac Newton, one of the greatest scientists of all times. Newton built on Galileo's ideas and laid the foundation of mechanics in terms of 3 laws of motion that go by his name. Galileo's law of inertia was his starting point, which he formulated as the first law of motion. So here is the first law of motion. every body continues to be in a state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. Let me repeat this first law of motion. Every body continues to be in a state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. The state of rest or uniform linear motion both imply zero acceleration. The first law of motion can therefore be simply expressed as if the net external force on a body is zero, its acceleration is zero. Acceleration can be non-zero only if there is a net external force on the body. Two kinds of situations are encountered in the application of this law in practice. In some examples, we know that the net external force on the object is zero. In that case, we can conclude that the acceleration of the object is zero. For example, a spaceship out in interstellar space, far from all other objects and with all its rockets turned off, has no net external force acting on it. Its acceleration, according to the first law, must be zero. If it is in motion, it must continue to move with a uniform velocity. Okay, so more often, however, we do not know all the forces to begin with. In that case, if we know that an object is unaccelerated, that is, it is either at rest or in uniform linear motion, we can infer from the first law that the net external force on the object must be zero. Gravity is everywhere. For terrestrial phenomena in particular, every object experiences gravitational force due to the earth. Also, objects in motion generally experience friction, viscous drag, etc. If then on earth an object is at rest or in uniform linear motion, it is not because there are no forces acting on it, but because the various external forces cancel out, that is, add up to zero net external force. Consider a book at rest on a horizontal surface as shown in figure 5.2. So here you can see a book at rest on a horizontal surface. It is subject to two external forces. The force due to gravity, that is its weight W, acting downward, and the upward force on the book by the table, the normal force R. R is a self-adjusting force. This is an example of the kind of situation mentioned above. The forces are not quite known fully, but the state of motion is known. We observe the book to be at rest. Therefore, we conclude from the first law that the magnitude of R equals that of W. A statement often encountered is, since W is equal to R, forces cancel out and therefore the book is at rest. This is incorrect reasoning. The correct statement is, since the book is observed to be at rest, the net external force on it must be zero, according to the first law. This implies that the normal force R must be equal and opposite to the weight W. Consider the motion of a car starting from rest, picking up speed, and then moving on a smooth straight road with uniform speed, as in the figure B. When the car is stationary, there is no net force acting on it. During pickup, it accelerates. This must happen due to a net external force. Note, it has to be an external force. The acceleration of the car cannot be accounted for by any internal force. This might sound surprising, but it is true. The only conceivable external force along the road is the force of friction. It is the frictional force that accelerates the car as a whole. You will learn about friction in section 5.9. Okay. When the car moves with constant velocity, there is no net external force. The property of inertia contained in the first law is evident in many situations. Suppose we are standing in a stationary bus and the driver starts the bus suddenly. We get thrown backward with a jerk. Why? Our feet are in touch with the floor. If there were no friction, we would remain where we were, while the floor of the bus would simply slip forward under our feet and the back of the bus would hit us. However, fortunately, there is some friction between the feet and the floor. If the start is not too sudden, that is, if the acceleration is moderate, the frictional force would be enough to accelerate our feet along with the bus. But our body is not strictly a rigid body, it is deformable. That is, it allows some relative displacement between different parts. What this means is that while our feet go with the bus, the rest of the body remains where it is due to inertia. Relative to the bus, therefore, we are thrown backward. As soon as that happens, however, the muscular forces on the rest of the body by the feet come into play to move the body along with the bus. A similar thing happens when the bus suddenly stops. Our feet stop due to the friction which does not allow relative motion between the feet and the floor of the bus. But the rest of the body continues to move forward due to inertia. We are thrown forward. The restoring muscular forces again come into play and bring the body to rest. Okay, here there is one example. An astronaut accidentally gets separated out of his small spaceship accelerating in interstellar space at a constant rate of 100 meter per second square. What is the acceleration of the astronaut the instant after he is outside the spaceship? Assume that there are no nearby stars to exert gravitational force on him. The answer is, since there are no nearby stars to exert gravitational force on him and the small spaceship exerts negligible gravitational attraction on him, the net force acting on the astronaut once he is out of the spaceship is zero. By the first law of motion, the acceleration of the astronaut is zero. So, with that, we come to an end of this topic, which is Newton's first law of motion. In my next video, I will read Newton's second law of motion. So don't forget to watch these videos, which I am sure will help in your studies. Although you need to study on a regular basis all the topics which is mentioned in your textbook and in your curriculum, but this will help you a little more. You can listen to it if you don't want to read, sometimes you can just listen to this video, right? So I hope it helps you in your studies. All the best to you. We will see in the next video. Thank you.